Welcome to P12 Waves Revision. So you'll be wondering first of all, what are waves? So waves transfer energy from one place to another without transferring any matter. Matter is the stuff, it's anything that is mass and volume and occupies a space. So for example, a car could be said to be made of matter. Waves transfer energy in the direction that the waves are traveling in. When waves travel through a medium or a material, the particles of the material oscillate or vibrate and transfer energy between each other, but overall the particles stay in the same place. They don't really move. Only energy is transferred, so the particles just vibrate. There are three very important properties of waves: the amplitude, wavelength and frequency. And we can represent a wave on a set of axes. We can have a line that is drawn to show the displacement of the particles from their undisturbed positions at a moment in time, so a snapshot. And that displacement is on the y-axis, and we can have the distance travelled by the wave on the x-axis. Okay, so it's just a snapshot taken of the wave at an instant. Now crests and troughs are just points of maximum positive and maximum negative displacement from the particle's rest position. Okay, so the crest will be the maximum positive displacement, and the trough of the wave will be the maximum negative displacement on that y-axis. Okay, so the first property that we need to know about is the amplitude, and the amplitude of the wave is the maximum displacement of a point on the wave from its undisturbed position, from its position of rest, in other words. It's basically the distance from the undisturbed position to a crest or a trough. The wavelength is the distance between the same point on two adjacent waves. Okay, so it could be the distance from one crest of a wave to the next crest of the wave, or it could be the distance from one trough of a wave to the next trough of a wave. Okay, so it's the distance from the same point on one wave to basically the same point on the neighboring wave. Okay, and finally the other property that we need to know about is frequency, and frequency is just the number of complete waves passing a certain point every second. Okay, now frequency is measured in a unit called hertz. Okay, and 1 hertz is basically 1 wave per second. So if we said 5 hertz, that would be 5 waves per second, would be the frequency of that wave. There's another important quantity which is called the period of a wave, and this is the amount of time it takes for a full cycle of the wave to pass a point. Okay, or a full cycle of the wave to be completed. In other words, it's the length of time between one crest passing a point and the next crest passing the same point. Okay, and you can find the period of a wave if you have the frequency using this equation where capital T is the period, time period, which is measured in seconds, and it's equal to 1 over the frequency, which is measured in hertz. Okay, so for example, if I had an object that had a frequency of 0.2 hertz and I needed to calculate the time period, then I would say that the time period is 1 over 0.2, which gives me 5 seconds. So the time period for an object with frequency 0.2 hertz would be 5 seconds. So the two types of waves exist. The first is called a transverse type of wave. Okay, And transverse waves are those waves where the oscillations or vibrations are perpendicular to the direction of energy transfer. Okay, so if these little circles represent the particles on a, let's say, a wave, could be generated by a slinky, for example, then we can see that the vibrations or the oscillations are up and down, and they are perpendicular to the direction of the wave or the direction in which the energy is being transferred of that wave. Now, examples of transverse waves include electromagnetic waves. Electromagnetic waves will be looked at a little bit later in another unit. An example of an electromagnetic wave could be light. Other examples of transverse waves include ripples and waves on the surface of water, and also waves on stretched strings, okay, such as guitar strings. The other type of wave is called a longitudinal wave, and longitudinal waves are those where the oscillations are parallel to the direction of energy transfer. So if we had a slinky spring over here, and we can see that the vibrations are parallel, or the oscillations are parallel to the transfer of energy, and where the slinky coils become very, very far apart, we call those regions rarefactions. Where the slinky coils, for example, or the waves get very close together, we call those regions of compression. Okay? Examples of longitudinal waves are sound waves in air, or ultrasound as well. So just the key thing to remember is that in longitudinal waves, the vibrations or oscillations are parallel to the direction of energy transfer. So the very important equation in waves is called the wave equation, and the wave equation is a way to give you the wave speed, which is the speed at which energy is being transferred in the wave. Okay, it's just basically how fast the wave is moving, and you can use the equation to work out the wave speed. Wave speed V is equal to the frequency of the wave multiplied by its wavelength lambda. Okay, and here is the formula triangle. Okay, you can see that the triangle is divided into two triangles, and the line that divides the triangle into two is the division line. Okay, so if you need to use the formula triangle, for example, if you wanted to find the wavelength, you cover your finger over the wavelength lambda symbol, and you can see that the wavelength is given by V divided by F. Very important also that you remember the units of wave speed. The unit of wave speed is meters per second. Recall that the frequency's unit is hertz, and wavelength is measured in meters. So here's an example of a question that you could be asked on the wave equation. It says that a radio wave has a frequency of 12.0 times 10 to the power 6 hertz. Find its wavelength if the speed of radio waves in air is 3.0 times 10 to the power 8 meters per second. So to find the wavelength, you need to first of all rearrange the equation, the wave equation, V is equal to F times lambda, and use your formula triangle if it helps, and you can see that lambda, the wavelength, is equal to the wave speed divided by the frequency. So you can substitute in the values for V and F to calculate lambda, which is the wavelength. So you see that the wavelength is equal to 3.0 times 10 to the power 8 divided by 12.0 times 10 to the power 6. Use your calculator to do that, and you should find that you get a value for the wavelength of this particular radio wave at 25 meters. You can use an oscilloscope, or sometimes called a cathode ray oscilloscope, CRO, to measure the speed of sound. Now this experiment can be performed by connecting basically a loudspeaker to a signal generator, okay, to basically generate the sound to be picked up by the two microphones. You select a specific frequency, let's say about 250 hertz on your signal generator, and the two microphones are connected to an oscilloscope, as you can see in the diagram, which picks up the sound from the speaker and which is converted to an electrical signal by the microphone and displayed as a trace on the cathode ray oscilloscope screen, as you can see there. You can secure the speaker and the two microphones with stands and clamps, making sure that they are aligned at the same height. Then set the oscilloscope to detect the sound wave signals from both microphones to give you two traces on the screen. So you can see two traces on the screen there. Start with the two microphones next to each other near the speaker. Okay. So there's our setup, and what we've got to do now is we slowly start to move one microphone. In this diagram it's microphone 2. Move it slowly away from the other one, which is the microphone 1, and when the two microphones are first exactly one wavelength apart, you'll see that the two signal traces on the oscilloscope are exactly aligned or synchronized. So there you can see microphone trace 1 and microphone trace 2 exactly aligned or synchronized. Okay, and then measure the distance between the microphones, and this will give you the wavelength of the sound, lambda. And then you can use the wave equation, V is equal to F times lambda, to find the speed of the sound waves that are passing through the air, because remember, you've got the frequency already set up on your signal generator. So you already know the frequency and you know the wavelength. So you can work out the speed of sound in air. Another experiment you need to know about is measuring the speed of water ripples using a lamp. Okay, so here's the diagram of the setup. So the illumination is the lamp. You dim the lights once you've set everything up, as you can see in the diagram, and turn on the lamp, and the motor, which causes this oscillating paddle you can see in the diagram, to move up and down. Sometimes this oscillating paddle is called a dipper, and it basically dips in and out of the shallow tank of water, which produces ripples. Okay, and you can adjust the frequency of the paddle, which is attached to a signal generator. You'll see a wave pattern that's made by the shadows of the wave. These shadows of waves are the wave crests, and they appear on the screen, which is below the tank. Okay, so this whole setup is called the ripple tank setup, and the distance between each shadow line is basically one wavelength. So you measure the distance between shadow lines that are 10 wavelengths apart, then divide this distance by 10 to find the average wavelength. So you now have the wavelength, and you also have the frequency. You could also do this by taking a photograph of the shadows with the ruler and find the wavelength from the photo instead, in exactly the same method. It might be a bit easier because obviously the waves are always moving. If you take a photograph, then everything's still. Use the wave equation again. V is equal to F times lambda to calculate the speed of the waves in the ripple tank. The final experiment that you need to know about is measuring the speed of waves on a stretched string. To do this, you need obviously a very taut string or tightly pulled string and a piece of kit which is called a vibration transducer. A vibration transducer will convert basically an electrical signal from a signal generator into vibrations. When it's attached to a taut string, waves are formed on the string. You can make sure that the string is very taut by connecting one end to the vibration transducer and passing it over a pulley, as you can see in the diagram, with masses hanging from the other end. This obviously will keep the string nice and taut. You set up the equipment as shown there. Turn on the signal generator and vibration transducer, and the string will start to vibrate as shown in the next diagram. So what you need to do is you need to adjust the frequency setting on the signal generator to change the length of the wave created on the string. Adjust the frequency until there appears to be a clear wave on the string. This happens when a whole number of half wavelengths fit exactly on the string. You probably want to create about 4 or 5 half wavelengths. That would be ideal. Now the frequency you need will depend on the length of the string between the pulley and transducer, and obviously the masses that you're using as well. So what you then need to do is you've created a number of half wavelengths on the string. In this diagram you can see 1, 2, 3, 4, 5, 6 half wavelengths. So measure the length of all of those 6 half wavelengths in one go. Then divide by the total number of half wavelengths, so whatever that length is on the ruler, divide it by 6 in this diagram to get the mean half wavelength. And obviously that's half a wavelength, so if you double this value you will get the full wavelength. So the frequency of the wave is given by whatever the signal generator is set to create this these number of half wavelengths. And then you can find the speed of the wave again using the important wave equation, v is equal to f times lambda. Now the final important topic that you need to know about for waves is refraction. Refraction is when light waves are basically bent as they enter a new media or a new material. For example, as light travels from air and it enters glass, okay, it will refract or bend. When a wave crosses a boundary between two materials, it changes speed. If the wave is traveling along the normal, which is the line that's drawn at 90 degrees to the boundary, then it will change speed, but it's not refracted. So there's no refraction taking place, but be careful because the wave speed will change. If the wave hits a boundary at a certain angle, then it will change direction, and that means it is refracted. The speed of the wave will also change. Now the wave bends towards the normal if it slows down, and it bends away from the normal if it speeds up. Now the higher the density of the material, the slower the wave travels through it. Okay, so if a material has a higher density, for example glass has a higher density than the air, then the wave will travel slower in the glass than it would in the air. Okay, now the wavelength of a wave changes when it is refracted, but the frequency always stays the same regardless of refraction taking place. So here's a little diagram for you. We've got these imaginary lines called wavefronts that are drawn through certain points on waves. For example, through each crest. They're always perpendicular to the direction in which the wave is moving, and so they're perpendicular to the line you've drawn in the ray diagram. Okay, so this particular, the first ray diagram at the top is a wavefront diagram showing light waves traveling along a normal to the boundary. The wavefronts are closer together in the more denser, higher density material, showing the decrease in the wavelength as it passes through the denser material such as glass in this case. Okay. In the other diagram, the second diagram, you can see there that the wavefronts are arriving at an angle, okay, and so they are refracted and they bend towards the normal, and then when they emerge at the other end out of the air again, they bend away from the normal. Okay. Now we can draw a ray diagram to show refraction. Rays are straight lines that are basically perpendicular to wavefronts. They show the direction a wave is traveling in, so you can draw a ray diagram of a refracted light ray as shown here. Here you have two mediums. One's the square could represent, the blue square could represent glass, for example. You've got an incident ray arriving at the block. You've drawn your normal line, which is 90 degrees to the boundary between, let's say, the air and the glass. And then you have a refracted ray. In this case, it's probably a more denser medium because it's glass, so it's bending towards the normal. And the important thing is the point where the ray of incident light hits the boundary is called the point of incidence, and the angle that the incident ray makes with the normal is called the angle of incidence, and the angle of refraction is the angle between the refracted ray and the normal line. Now, here are some questions for you to have a go at, so you can pause the video and try these questions. Here are the answers to those questions, and again, you can pause the video to check how you got on. Here are a few more questions for you to have a go at, so you can again pause the video and try some of these questions to practice. Here are the answers to question number 5 and question number 6, so you can pause the video and see how you got on to mark your answers. Here are some slightly more challenging questions for you to have a look at. Again, you can pause the video here. This is question number 8, continued. It's got part A and part B, so you can pause the video and have a go at this question. Here are the answers to question number 7 and question number 8, so you again can pause the video and see how you got on. Thank you very much for listening to this and watching this lesson.